4 light-years away sits the closest Sun-like star system to Earth. We've known about Alpha Centauri for thousands of years. We named it, charted it, pointed every generation of telescope at it, and assumed that because it was close, it was familiar. Then the James Webb Space Telescope looked at it for the first time using its mid-infrared eye, and something appeared in the data that should not have been there. A faint point of light, 10,000 times dimmer than the star, sitting right inside the habitable zone. And then, months later, it vanished. Webb did not find comfort at our nearest sun-like neighbour. It found a disappearing world, blinding glare, and the unsettling realization that proximity never meant understanding. If you enjoy journeys that change how you see reality, hit that like button and subscribe. And if you'd like to listen to us whilst on the move, we're now live on Spotify. The link is in the description. Now, settle in and get yourself comfortable. Let's begin. There is a star system so close to Earth that its light reaches us faster than an Amazon package crosses the Pacific Ocean. 4.3 light-years. That is the distance separating our solar system from Alpha Centauri. In cosmic terms, this is not a neighbour. This is a roommate. This is someone sharing the same hallway, breathing the same recycled air, close enough that you would recognise their footsteps at 3 in the morning. Alpha Centauri is the nearest stellar system containing Sun-like stars, not the nearest star overall. That title belongs to Proxima Centauri, a dim red dwarf so faint you cannot see it without a telescope, despite it being slightly closer at 4.24 light-years. But Proxima is a tiny ember compared to the 2 stars that dominate the Alpha Centauri system. Alpha Centauri A and Alpha Centauri B are both genuine Sun-like stars. One is slightly larger and brighter than our Sun. The other is slightly smaller and cooler. Together with Proxima, they form a triple star system that has been visible to human eyes since our species first looked up. This system sits in the constellation Centaurus, blazing as the 3rd brightest star in the entire night sky. Ancient navigators steered by it. Aboriginal Australians wove it into creation stories. Ptolemy catalogued it in the 2nd century. Every civilization with a clear view of the southern sky knew this star. We have been staring at Alpha Centauri for thousands of years, and because we have been staring at it for so long, and because it is so close, most people carry an unconscious assumption about this system. The assumption is simple and feels perfectly reasonable. It goes like this. Alpha Centauri is nearby. It is bright. It is made of sun-like stars. We have been observing it for centuries with progressively better instruments. Therefore, we must understand it fairly well. It must be one of the most thoroughly characterized stellar systems in the galaxy. Whatever secrets it holds, surely we cracked them long ago. That assumption is wrong, and the James Webb Space Telescope just proved exactly how wrong it is. But before we get to what Webb found, you need to understand what Alpha Centauri actually is, because most people get this wrong too. They hear nearest star and picture a single point of light sitting alone in space. The reality is far more complex. Alpha Centauri is a triple star system, but it is not 3 stars casually drifting through the same neighbourhood. Alpha Centauri A and Alpha Centauri B are locked in a tight gravitational embrace. They orbit each other once every 79.9 years along an elliptical path that brings them as close as 11 astronomical units apart and swings them as far as 36 astronomical units from each other. For reference, 11 astronomical units is roughly the distance from our Sun to Saturn. 36 astronomical units is close to the distance from our Sun to Pluto. These 2 stars spend their entire existence dancing around a shared centre of gravity, sometimes close enough to disrupt each other's planetary neighbourhoods, sometimes far enough apart that each star briefly gets room to breathe. Then there is Proxima Centauri, the 3rd member of the system. Proxima orbits the central pair at a staggering distance of roughly 13,000 astronomical units. That is about 1/5 of a light-year. Proxima is so far from Alpha Centauri A and B that it takes over 500,000 years to complete a single orbit around them. Some astronomers have even debated whether Proxima is truly gravitationally bound to the pair, or merely passing through on an extremely slow trajectory. Current evidence suggests it is bound, but barely. Proxima clings to the system like a distant suburb connected to a city by a single crumbling road. Now, here is what matters about these stars individually. Alpha Centauri A is a G-type main sequence star. That is the same spectral classification as our Sun. It is about 10% more massive than the Sun, roughly 23% larger in diameter, and approximately 50% more luminous. If you swapped our Sun for Alpha Centauri A, Earth would receive more light and heat, but the star itself would look and behave in ways that feel deeply familiar. It burns hydrogen in its core through the same fusion processes. It has a similar surface temperature. It is slightly older than our Sun, estimated at approximately 5 to 6 billion years old, making it a mature star at a comparable stage of its hydrogen-burning life. Alpha Centauri A is, for all practical purposes, our Sun's near twin. Alpha Centauri B is a K-type star, slightly cooler and dimmer. It carries about 90% of the Sun's mass and emits roughly half its luminosity. It is smaller and less imposing than its partner, but still a legitimate Sun-like star by any reasonable definition. Together, these two stars represent the closest binary pair of Sun-like stars in the galaxy relative to Earth. This is why Alpha Centauri matters so much. It is not just the nearest stellar system. It is the nearest system where we might expect to find planetary conditions remotely similar to our own. A Sun-like star at the right age, with the right chemistry, at a distance close enough for detailed study. If planets exist around Alpha Centauri A or B, they would be the most accessible exoplanets in the entire galaxy for follow-up observation. Every astronomer who has ever dreamed of characterizing an alien world in detail has looked at Alpha Centauri and thought the same thing. This is where we start, and humanity has treated it exactly that way. Alpha Centauri is the default destination for nearly every serious interstellar travel concept ever proposed. The Breakthrough Starshot initiative, backed by billions of dollars in funding, aims to send gram-scale spacecraft to Alpha Centauri at 20% the speed of light, reaching the system within roughly 20 years of launch. Science fiction has used Alpha Centauri as a setting so frequently that the name carries an almost domestic quality. It feels like a place we already know, a cosmic suburb just down the road, the house next door. Alpha Centauri's grip on human imagination runs deeper than most people realize. It is not merely a well-known star. It is the default answer to one of humanity's oldest questions. If we ever leave the solar system, where do we go first? The answer, for over a century of scientific and fictional speculation, has been the same: Alpha Centauri. Always Alpha Centauri. By the mid-20th century, science fiction writers had already established Alpha Centauri as the default interstellar destination, and the tradition has only deepened since. Since then, the list of novels, films, and television series set at Alpha Centauri has grown into something closer to a cultural tradition than a creative choice. James Cameron's Avatar placed its fictional moon, Pandora, in orbit around a gas giant in the Alpha Centauri system. The franchise has generated billions of dollars in revenue, and for a significant portion of the global population, Alpha Centauri is synonymous with that single fictional world. The original Lost in Space television series launched in 1965, with Alpha Centauri as the Robinson family's explicit destination, embedding the system in popular culture for generations. The landmark Chinese science fiction novel The Three-Body Problem by Liu Cixin uses Alpha Centauri as the home system of an alien civilization. The strategy game series Civilization has sent players to Alpha Centauri as the ultimate endgame achievement for decades. These are not obscure references. They represent mainstream cultural touchstones that have shaped how hundreds of millions of people think about interstellar space. And every single one of them reinforces the same implicit message. Alpha Centauri is reachable. Alpha Centauri is knowable. Alpha Centauri is where we go next. The scientific community has echoed this cultural assumption with its own set of ambitious proposals. Breakthrough Starshot, announced in 2016, with backing from investor Yuri Milner and the late physicist Stephen Hawking, aims to send fleets of gram-scale spacecraft propelled by ground-based lasers to Alpha Centauri at 20% the speed of light. At that velocity, the journey would take roughly 20 years. with data returning to Earth after another 4 years of light travel time. Within a single human lifetime, we could have close-up images of whatever orbits the nearest Sun-like stars. Other proposals have been even more ambitious. Project Longshot, studied by the United States Naval Academy in the late 1980s, envisioned an unmanned, fusion-powered probe making the crossing in 100 years. The British Interplanetary Society's Project Daedalus designed a 2-stage fusion starship capable of reaching Barnard's star within 50 years, demonstrating that nearby stellar systems, including Alpha Centauri, were within the reach of fusion propulsion concepts. More recently, proposals for laser sail propulsion, antimatter engines, and even generation ships carrying permanent human populations have all defaulted to Alpha Centauri as their destination. The system is so thoroughly embedded in interstellar mission planning that choosing a different target feels almost contrarian. This cultural and scientific fixation matters because it has created an emotional baseline. People do not just know about Alpha Centauri, they feel they have a relationship with it. It is the star system that appears in their movies, their games, their news feeds about breakthrough propulsion research. It carries a warmth that no other stellar system possesses. Sirius is brighter but feels alien. Vega is famous but remote. Alpha Centauri feels almost domestic, like a vacation home that the family has been planning to visit for generations but has never quite managed to reach. And that emotional baseline is precisely what makes Webb's ambiguous results so destabilizing. When you have spent decades treating a place as the obvious first destination, as the neighbor you already understand, and then the most powerful telescope ever built looks at it and comes back with a mystery rather than an answer, the dissonance cuts deeper than a purely scientific result normally would. It is not just data that fails to resolve. It is an expectation, a cultural narrative, a story we have been telling ourselves for generations. The crack in that story was always there. It just took Webb to make it visible. But here is the crack in that comfortable image. Despite all the attention, despite all the telescopes, despite centuries of observation and decades of modern exoplanet science, we have never confirmed a single planet orbiting either Alpha Centauri A or Alpha Centauri B. Let that settle for a moment. We have discovered and confirmed over 6,000 exoplanets orbiting other stars across the galaxy. We have found planets around stars thousands of light years away. We have detected worlds smaller than Earth in systems so distant that their host stars appear as faint smudges even in our most powerful telescopes. Yet the nearest pair of Sun-like stars, sitting right next door at 4 light-years, has yielded 0 confirmed planets. Proxima Centauri, the dim red dwarf third wheel, has done better. Astronomers have confirmed 3 planets orbiting Proxima. Proxima Centauri B sits in the habitable zone and has attracted enormous attention as a potentially rocky world. But Proxima is a completely different kind of star. It is a red dwarf, tiny, cool, and prone to violent stellar flares that may strip the atmosphere from any planet orbiting too close. Proxima's planets are scientifically fascinating, but they do not answer the question that burns brightest. Do Sun-like stars in the nearest system host worlds of their own? This absence is not for lack of trying. Astronomers have been hunting for planets around Alpha Centauri A and B for decades, using every major detection method available. The results have been a humbling parade of false starts, contested signals, and retracted claims. The most famous example came in 2012. A European team announced the discovery of an Earth-mass planet orbiting Alpha Centauri B with a period of just 3.24 days. The planet was designated Alpha Centauri B. Headlines exploded. The nearest Sun-like star had an Earth-sized world. It was exactly the discovery everyone had been waiting for. Except it was not real. Subsequent analysis by independent teams revealed that the signal was almost certainly an artifact of the data processing. The detection method, radial velocity, measures tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. But the Alpha Centauri binary system creates its own complex gravitational signature that contaminates the data. Disentangling the subtle wobble of a small planet from the overwhelming gravitational noise of 2 Sun-like stars orbiting each other turned out to be far harder than anyone anticipated. The planet was retracted, the signal vanished, Alpha Centauri B became one of the most prominent false positives in exoplanet history. Other attempts fared no better. Radial velocity surveys continued, pushing sensitivity to lower masses, but the binary contamination remained a persistent obstacle. Transit searches, which look for tiny dips in starlight as a planet crosses in front of its star, found nothing conclusive. The Hubble Space Telescope observed the system. Ground-based observatories targeted it with adaptive optics. Each campaign returned the same frustrating answer: no confirmed planets. This is where the story takes a turn that most people do not expect. The reason we have failed to find planets around Alpha Centauri A and B is not that the system is too far away. The reason is almost the opposite. The system is too close, too bright, and too complicated. Think about what an astronomer faces when pointing a telescope at Alpha Centauri. You are aiming at the third brightest star in the night sky. Alpha Centauri A blazes with such intensity that its light overwhelms sensitive detectors designed to pick up faint planetary signals. It is like trying to spot a candle flame taped to the side of a lighthouse. The lighthouse is so blindingly bright that the candle becomes invisible, not because the candle is not there, but because the light drowns everything. Now add a second lighthouse right next to the first one. That is Alpha Centauri B. The two stars are separated by a distance that varies between roughly 4 and 22 arcseconds, as seen from Earth, depending on where they are in their 80-year orbit. For context, 22 arcseconds is a tiny angle, roughly the apparent width of a small coin seen from a quarter-mile away. When the stars are at their closest separation, their light blends together in telescope images, creating a blinding combined glare that obliterates any hope of seeing faint objects nearby. This brightness problem affects every detection method differently. For radial velocity, the binary's gravitational signal creates noise that mimics planetary wobbles. For transit photometry, the combined stellar brightness reduces the relative depth of any planetary transit to levels below current detection thresholds. For direct imaging, the star's glare creates diffraction patterns, scattered light, and optical artifacts that can look exactly like faint point sources. Every approach runs into the same fundamental wall. Alpha Centauri is too luminous and too complex for the tools we have been using. This is the cruel irony of our nearest sun-like neighbour. Its proximity, which should make it the easiest stellar system to study, actually makes it one of the hardest. Distant stars do not have this problem. A sun-like star 100 light-years away is dim enough that sensitive instruments can detect planetary signals without being overwhelmed. The farther a star is, the fainter it appears, and the easier it becomes to isolate subtle planetary signatures from stellar noise. Alpha Centauri breaks this pattern because it sits so close that its brilliance becomes a barrier rather than an advantage. Imagine you are an astronaut trying to photograph a firefly. If the firefly hovers in a dark field at night, the task is straightforward. Point your camera, open the shutter, capture the faint glow against the black background. Now imagine the firefly is hovering 6 inches from a stadium floodlight. The floodlight's glare washes out everything around it. The firefly is still there, still glowing, but your camera cannot separate its faint light from the overwhelming brilliance beside it. That is the problem with Alpha Centauri. The planets might be there, they might even be common, but the stars are screaming so loudly that we cannot hear anything else. And this is exactly why the James Webb Space Telescope's decision to observe Alpha Centauri mattered so much. Webb was not just pointing a fancy new telescope at a familiar target, it was attempting something that every previous observatory had failed to accomplish. It was trying to see through the glare of the nearest sun-like star system using an instrument specifically designed to suppress starlight and reveal what hides beneath. Webb carries an instrument called MIRI, the mid-infrared instrument. MIRI operates at wavelengths of light that human eyes cannot see, deep in the infrared spectrum where warm objects glow brightly, but sun-like stars emit relatively less of their total energy. This wavelength choice is strategic. In visible light, a sun-like star outshines a nearby planet by factors of billions. In the mid-infrared, that contrast ratio drops dramatically. A warm gas giant still glows faintly in infrared, and the star's relative brightness decreases. The difference between star and planet shrinks from impossible to merely incredibly difficult. MIRI also includes a coronagraph, a device that places a tiny physical mask directly over the star's image inside the instrument. The mask blocks the star's central light, creating an artificial eclipse that lets astronomers search for faint objects lurking in the star's immediate vicinity. Coronagraphs have been used on other telescopes before, but MIRI's coronagraph operates in the mid-infrared from the ultra-stable environment of deep space, giving it advantages that ground-based instruments cannot match. But even with MIRI's coronagraph, observing Alpha Centauri remained what the research team called incredibly challenging. The stars are bright. They are close together on the sky. They move across the sky quickly due to their proximity, requiring custom tracking procedures. The standard Webb target acquisition process, the automated system the telescope normally uses to lock onto a star, does not work for Alpha Centauri A because the star is simply too bright. The operations team at the Space Telescope Science Institute had to develop an entirely custom observing sequence just for this one target. And there was another problem that no coronagraph could easily solve. Even if you perfectly block Alpha Centauri A's light, there is still the problem of Alpha Centauri B blazing away at a different position in the field of view. No single coronagraphic mask can block both stars simultaneously. Dealing with that second source of contamination would require computational techniques that push the data processing to its absolute limits. This is what makes Webb's observation of Alpha Centauri fundamentally different from a routine exoplanet survey. This was not point, shoot, and discover. This was a carefully orchestrated assault on one of the most technically forbidding targets in the sky. Every step involved overcoming a unique obstacle that exists specifically because Alpha Centauri is so close and so bright. The team was not leveraging proximity as an advantage. They were fighting against it, and yet they attempted it anyway. Because the scientific payoff of success would be extraordinary. If Webb could directly image a planet around Alpha Centauri A, it would be the closest directly imaged exoplanet in history. It would orbit the nearest Sun-like star to Earth. It would be accessible for follow-up characterization in ways that no other exoplanet could match. Every atmospheric measurement, every orbital refinement, every search for moons or rings would be easier and more detailed than for any other known world outside our solar system. The prize was worth the pain. In August of 2024, the James Webb Space Telescope turned its mid-infrared eye toward Alpha Centauri A. The custom observing sequence is activated. The coronagraphic mask slid into place over the star's blazing image. Reference star observations were collected. Computational pipelines began stripping away the layered glare of both stars, peeling the data like an onion, searching for anything faint and unexpected beneath. What emerged from that data did not simplify our understanding of the nearest Sun-like stellar system. It shattered the assumption that proximity meant familiarity. It introduced a mystery that, as of right now, remains unresolved, and it forced astronomers to confront an idea that most people have never considered. The nearest major stellar neighbour is not a solved point of light. It is not a familiar address where we know exactly what sits in the yard. It is a place we have been staring at for millennia without truly seeing. And when we finally built an instrument powerful enough to look beneath the glare, what we found was not the comfortable confirmation we expected. It was a disappearing world. A candidate planet that appeared once, then vanished. A signal strong enough to demand attention but elusive enough to resist confirmation. And behind it, the growing suspicion that Alpha Centauri has been hiding structure in plain sight all along. What Webb actually saw, and why the planet vanished, is a story that rewrites everything we thought we knew about our nearest sun-like neighbour. The hardest part of what Webb did at Alpha Centauri was not the science, it was the pointing. Every observation the James Webb Space Telescope performs begins with a process called target acquisition. The telescope's guidance system locks onto the intended star, centers it precisely within the instrument's field of view, and confirms alignment before data collection begins. This procedure is automated, reliable, and has worked flawlessly for thousands of targets since Webb began science operations in 2022. It is a routine step, like a surgeon washing their hands before an operation. Essential, but rarely the part anyone worries about. For Alpha Centauri A, target acquisition failed before it even started. The star is simply too bright. Alpha Centauri A is the brightest component of the third most luminous star in Earth's night sky, and Webb's guidance sensors are designed for objects dramatically fainter. Pointing the telescope directly at Alpha Centauri A and asking the standard acquisition system to lock on would be like asking a camera designed for candlelit portraits to photograph the surface of the Sun. The sensors would saturate instantly, flooding the electronics with so much light that the telescope could not determine where the star was centered. The automated system was useless, so the operations team at the Space Telescope Science Institute invented a workaround. Instead of acquiring Alpha Centauri A directly, they used a technique called a blind offset. They pointed Webb at a different star, one bright enough for the guidance sensors to handle but not so overwhelming that it caused problems. That reference star was Epsilon Muscae, a red giant located roughly 330 light-years from Earth in the constellation Musca. Epsilon Muscae has a luminosity about 1,700 times that of the Sun, which sounds extreme, but at its much greater distance it appears manageable to Webb's sensors. The team locked onto Epsilon Muscae, confirmed precise alignment, then commanded the telescope to slew a pre-calculated angular distance to where Alpha Centauri A should be, trusting their math to place the star behind the coronagraphic mask, without ever directly seeing it through the guidance system. This is the astronomical equivalent of trying to park a car in a specific spot while blindfolded, using only the knowledge that the parking space is exactly 47 steps to the left of a lamppost you touched 3 minutes ago. The precision required is extraordinary. The margin for error is measured in fractions of an arcsecond. If the offset calculation is wrong by even a tiny amount, Alpha Centauri A lands slightly off-center behind the coronagraphic mask, and starlight leaks around the edges, destroying the observation. The operations team pulled it off. The custom sequence worked. Alpha Centauri A landed behind the mask, but the difficulty of this single preparatory step reveals something important about the nature of this observation. Webb was not casually glancing at an easy nearby target. It was stretching its operational limits to observe one of the most technically hostile objects in the sky. With Alpha Centauri A positioned behind the coronagraphic mask, MIRI began collecting mid-infrared light at 15.5 microns. At this wavelength, deep in the infrared spectrum far beyond what human eyes can detect, the contrast between a sun-like star and a warm giant planet shrinks considerably compared to visible light. A gas giant with a temperature of a few hundred degrees radiates strongly in the mid-infrared. The host star still dominates, but by a factor of thousands rather than billions. This wavelength choice was deliberate, strategic, and essential. Without it, the observation would have been pointless. But blocking Alpha Centauri A's light was only half the battle. The coronagraph does not produce a clean black circle where the star used to be. Instead, it creates a complex pattern of residual light. The way photons bend around the edges of the physical mask generates rippling diffraction patterns that spread outward from the blocked star like waves in a pond. The telescope's own optical structure, its mirrors, support struts, and internal baffles, causes some light to scatter and interfere with itself, producing circular rings and spoke-like features radiating across the image. These artifacts look disturbingly like faint point sources. A bright spot in a diffraction ring can mimic a planet. A spike in scattered light can masquerade as a distant object. The image after coronagraphic masking is not a clean photograph. It is a minefield of optical illusions that must be navigated with extreme care. And then there is Alpha Centauri B. The coronagraph blocks one star. It cannot block two. Alpha Centauri B sits nearby in the field of view, blazing with its own considerable luminosity, pouring additional light across the detector. This second star creates its own set of diffraction patterns, its own scattered light, its own artifacts, all overlapping with the residual light from Alpha Centauri A. The combined contamination from both stars transforms the image into a layered mess of competing optical signals. To deal with this, the team employed a multi-stage subtraction process. First, they observed reference stars with similar brightness and spectral properties to build models of what the coronagraphic artifacts should look like for a star alone. Then they subtracted those modeled artifacts from the Alpha Centauri data. Next, they used computational algorithms to model and remove the contribution of Alpha Centauri B's light, effectively erasing the second star from the image. Each subtraction step peeled away another layer of stellar contamination, gradually revealing whatever faint signals might be hiding beneath. After all of this processing, something appeared. In the August 2024 data, after the light from both stars had been painstakingly removed, a faint point source emerged. It sat at a projected separation of roughly 2 astronomical units from Alpha Centauri A, positioned in a region of the image where the subtraction algorithms had performed cleanly and artifact contamination was minimal. The source was designated SOHN. SOHN was faint, extraordinarily faint. It was more than 10,000 times dimmer than Alpha Centauri A at the observation wavelength. To put that ratio into perspective, if Alpha Centauri A were a concert arena packed with 10,000 screaming fans, SOHN would be a single person whispering in the back row. The team had detected that whisper, but detecting a faint point source near a bright star is not the same as discovering a planet. The history of exoplanet science is littered with faint blobs that turned out to be artifacts, background galaxies, foreground objects, or processing errors. The team knew this. They subjected SOHN to an extensive battery of tests designed to determine whether the source was real or illusory. Could SOHN be a background star or galaxy? The team checked. Alpha Centauri moves across the sky rapidly due to its proximity, which means background objects would shift position relative to the star between observations taken months or years apart. The team compared their data with archival images and found no known background source at that position. Could it be a foreground object, like an asteroid in our own solar system drifting through the field of view? The geometry and expected brightness of solar system objects at that position made this explanation unlikely. Could it be an instrumental artifact, a ghost image created by the telescope's optics? This question was harder to dismiss. Normally, astronomers use a technique called angular differential imaging to separate real objects from artifacts. The telescope observes the target, then rolls slightly along its line of sight and observes again. Real astronomical objects rotate with the sky, shifting position in the image as the telescope rolls. Artifacts tied to the telescope's optics stay fixed. By comparing the 2 rolled observations, astronomers can identify which sources are real and which are instrumental phantoms. This technique is a standard tool for direct imaging exoplanet searches. For the August 2024 observation of Alpha Centauri, the roll maneuvers did not work as intended. The telescope performed the rolls, but complications in the observation sequence meant the team could not cleanly apply angular differential imaging to definitively separate SOHN from potential artifacts. This was not a catastrophic failure. The team performed extensive alternative analyses, testing SOHN's properties against known artifact patterns, checking its brightness and position for consistency with instrumental effects, running statistical tests to assess the probability of a false detection. Their conclusion was that SOHN was unlikely to be an artifact. It was also unlikely to be a background or foreground source. The most probable explanation was that it represented a real astrophysical object associated with Alpha Centauri A, but unlikely to be an artifact is not the same as definitely a planet. The team was careful with their language, and this caution matters. SOHN was classified as a candidate. Strong evidence, but not confirmation. If SOHN is a planet, what kind of world would it be? The team's analysis, published in 2 companion papers accepted by the astrophysical journal Letters, paints a preliminary portrait. Based on its brightness at 15.5 microns and its projected separation from the star, SOHN is most likely a gas giant with a mass roughly comparable to Saturn. It orbits Alpha Centauri A at a distance that varies between approximately 1 and 2 astronomical units, following an elliptical path through the star's habitable zone. Its orbital period is estimated between roughly 1.5 and 3 Earth years. Its orbit appears significantly inclined relative to the orbital plane of the Alpha Centauri A and B binary, tilted by roughly 50 to 130 degrees. This is not an Earth-like world. It is a gas giant, a massive ball of hydrogen and helium without a solid surface, incapable of supporting life as we understand it. But its location is remarkable. It sits inside the habitable zone of the nearest Sun-like star to Earth. If confirmed, it would be the closest directly imaged exoplanet ever detected. It would be the nearest planet orbiting in the habitable zone of a Sun-like star. It would be, as one researcher involved in the study described it, potentially the most significant James Webb Space Telescope discovery to date. To understand why that phrase carries such weight, you need to see where SONE would sit in the history of exoplanet science if it is confirmed. The first exoplanet discovered around a Sun-like star was 51 Pegasi b, detected in 1995 by Swiss astronomers Michel Mayor and DDA Kalo through the radial velocity method. That single detection launched an entirely new field of astronomy. In the 3 decades since, nearly 6,000 exoplanets have been confirmed across the galaxy, orbiting stars of every type at distances ranging from a few light-years to thousands. The pace of discovery has been extraordinary, transforming exoplanet science from a speculative frontier into one of the most data-rich branches of modern astrophysics. But there is an important subtlety hidden in those numbers. The vast majority of confirmed exoplanets were detected indirectly. Radial velocity measures the wobble of the star. Transit photometry measures the dimming of the star. In both cases, the planet itself is never seen. It is inferred from its effect on something else. The planet is a shadow, a tug, a dip in a light curve, real, confirmed, but invisible. Direct imaging, the method Webb used at Alpha Centauri, is fundamentally different. You photograph the planet. You see it as a distinct point of light, separated from its host star. This sounds like it should be the simplest approach, but it is by far the hardest. The contrast between a star and its planets is so extreme that only a handful of worlds have ever been directly imaged. Almost all of them are young, scorching hot super-Jupiters, orbiting far from their stars. Worlds like those in the HR 8799 system, or Beta Pictoris b. These are massive planets glowing with the residual heat of their formation, bright enough to stand out against their host stars at wide separations. SONE would shatter every record in the direct imaging catalogue. It would be the coldest directly imaged exoplanet, a world at temperatures of a few hundred degrees rather than over 1,000. It would be the lowest mass directly imaged exoplanet, roughly Saturn's mass compared to the multiple Jupiter mass behemoths in existing detections. It would be the closest directly imaged exoplanet to its host star in terms of physical separation, sitting at 1 to 2 astronomical units rather than the tens or hundreds of astronomical units typical of current direct imaging targets. And it would be the nearest directly imaged exoplanet to Earth, orbiting a star just 4 light-years away rather than dozens or hundreds. Any one of these records would make the detection significant. Holding all 4 simultaneously would make it historic. This is why the astronomical community has responded to an ambiguous, unconfirmed candidate with such intensity. The stakes of confirmation are not merely incremental. They would represent a categorical expansion of what direct imaging can achieve, proving that the technique can reach habitable zone planets of moderate mass around Sun-like stars at close range. The method that has so far captured only the brightest, hottest, most distant gas giants would suddenly have touched the regime that matters most for understanding planetary systems like our own. But here is where the story takes a turn that nobody anticipated. The team needed more data. One detection, however compelling, is not enough in science. Extraordinary claims require extraordinary evidence, and a planet around the nearest Sun-like star qualifies as extraordinary. The researchers secured additional Webb observing time through the Director's Discretionary Time program, a mechanism that allows urgent or time-sensitive observations outside the normal proposal cycle. They pointed Webb at Alpha Centauri A again in February 2025. They observed again in April 2025. Both observations used the same instrument, the same coronagraphic mode, the same processing pipeline. SONE was gone. In both follow-up observations, the faint point source that had appeared so clearly in August 2024 was nowhere to be found. The team checked their processing. They verified their subtraction algorithms. They examined the data for any systematic difference between the August observation and the later ones. The February and April data were clean. The observations worked. The instrument performed normally. SONE simply was not there. "We are faced with the case of a disappearing planet," said Arnie Ketsangi, a doctoral student at Caltech and co-first author on the discovery papers. The phrase captures both the mystery and the scientific tension perfectly. A candidate world had appeared once and then vanished twice. This is the moment where a lesser team might have quietly shelved the result and moved on. A single detection followed by two non-detections does not inspire confidence. In many scientific contexts, this pattern suggests the original signal was spurious, an artifact that happened to survive one round of processing but not the next two, a statistical fluctuation that mimicked a real source. The safe interpretation was that SOHN was probably not real, but the team did not stop there. They turned to orbital mechanics. If SOHN is a real planet on an elliptical orbit, it does not remain stationary relative to the star. It moves. At some points in its orbit, it swings far enough from Alpha Centauri A to be visible in coronagraphic images. At other points, it passes too close to the star, falling inside the region where the coronagraph's residual light overwhelms any faint source. At still other points, it might pass behind or in front of the star from our perspective, becoming geometrically undetectable regardless of instrument sensitivity. The team ran computer simulations modeling millions of possible orbits consistent with the August 2024 detection. They asked a precise question. For each simulated orbit, would the planet have been visible during the February and April 2025 observation windows? The answer was striking. In 52% of the stable orbits simulated, the planet moved too close to Alpha Centauri A during both follow-up windows. It would have been swallowed by the coronagraph's residual glare, invisible to Webb, even though it was still there. The non-detections were not evidence against the planet. They were consistent with a real world that had simply moved to a part of its orbit where the instrument could not see it. This result does not confirm the planet. It prevents the non-detections from killing the hypothesis. There is a significant difference. The team is not claiming they found a planet and then lost it. They are claiming they found a candidate. It disappeared in follow-up observations, and orbital modelling shows that disappearance is consistent with a real planet on a plausible orbit. The candidate survives. It does not graduate to confirmation. The orbital modelling that kept the candidate alive deserves a closer look, because it reveals how much scientific information can be extracted from the interplay between detections and non-detections when the analysis is rigorous enough. The team did not simply note that the planet could have moved behind the star. They constructed a comprehensive statistical framework. Starting with the August 2024 detection, they defined the candidate's position relative to Alpha Centauri A, its brightness, and the range of orbital parameters consistent with that single data point. A single snapshot of a planet's position constrains its orbit only loosely. You know where it was at one moment, but not how fast it was moving, in what direction, or on what shape of ellipse. Millions of different orbits could pass through that same point in space at that same time. So the team generated those millions of orbits. Each simulated orbit was assigned a random eccentricity, inclination, longitude of ascending node, argument of periapsis, and orbital period drawn from physically plausible distributions. For each orbit, the simulation calculated where the planet would have been during the February 2025 observation window. Then it calculated the position during the April 2025 window. For each window, the simulation asked a binary question. Would the planet have been far enough from Alpha Centauri A to be visible through the coronagraph, or would it have fallen inside the inner working angle where residual starlight overwhelms everything? The inner working angle is a critical concept. Every coronagraph has a minimum angular separation below which it cannot suppress starlight effectively. For MIRI's coronagraph at 15.5 microns, this limit corresponds to roughly 0.5 astronomical units at Alpha Centauri's distance. Any planet orbiting closer than that projected separation from the star at the moment of observation is invisible, swallowed by the zone of residual glare that the coronagraph cannot fully remove. The planet does not need to be physically close to the star. It only needs to appear close from Earth's perspective. A planet on a tilted eccentric orbit can swing through regions of its path where its projected separation from the star, as seen from Earth, drops below the coronagraph's inner working angle, even while its true physical distance from the star remains relatively large. This geometric subtlety is what makes the 52% figure so significant. More than half of the stable orbits consistent with the August detection naturally produce periods where the planet's projected separation falls inside the coronagraph's blind zone. The February and April windows happen to coincide with exactly such periods for a large fraction of those orbits. The planet was not necessarily behind the star in three-dimensional space. It may have been beside it, above it, or below it in physical terms. But from Earth's vantage point, it appeared too close to the star's position on the sky for the coronagraph to separate their light. The team then applied additional constraints. They required the simulated orbits to be dynamically stable within the Alpha Centauri binary system. Not every orbit that passes through the detected position is physically viable. The gravitational influence of Alpha Centauri B imposes strict limits on which orbits can survive for billions of years without being disrupted. Orbits that extend too far from Alpha Centauri A cross into regions where Alpha Centauri B's gravity dominates, scattering the planet out of the system entirely. Orbits with certain inclinations relative to the binary plane experience long-term perturbations called Kozai-Lidov, oscillations that can pump eccentricity to extreme values, eventually driving the planet into the star or ejecting it. After filtering for dynamical stability, the surviving orbits clustered around specific parameter ranges, orbital periods between roughly 1.5 and 3 years, eccentricities centered around 0.4, inclinations significantly tilted relative to the binary orbital plane. These are not arbitrary numbers. They are the solutions that simultaneously explain where the planet was seen, where it was not seen, and how it could survive in a binary system for the age of the stars. The elegance of this approach lies in what it transforms. Two non-detections, which initially seemed like evidence against the planet, become additional data points that constrain the orbit. Every observation window where the planet was not seen eliminates the subset of orbits that would have placed the planet in a visible location during that window. The detections tell you where the planet was, the non-detections tell you where it was not. Together, they carve away impossible orbits and leave behind the ones that are consistent with everything observed. This is a style of reasoning that would have been impossible a generation ago. The computational power required to simulate millions of orbits, test each one against multiple observation epochs, filter for dynamical stability in a binary system, and compile the statistical results into probability distributions simply did not exist. The candidate planet at Alpha Centauri A is as much a product of modern computational astrophysics as it is of Webb's infrared optics. But the story deepens further. The team revisited an earlier observation that most people had forgotten. In 2019, a different group of astronomers using the Very Large Telescope, a ground-based observatory operated by the European Southern Observatory in Chile, had observed Alpha Centauri A using a different infrared instrument. That observation also revealed a faint source near the star, designated Cone. The 2019 detection was intriguing, but inconclusive. It could have been a planet, a clump of zodiacal dust, or an instrumental artifact. The observation arc was too short to determine the source's nature, and without follow-up confirmation, the result languished in the scientific literature as an unresolved hint. The 2019 observation deserves its own telling, because it represents the first chapter of a story that most people have never heard. In 2019, a team led by Kevin Wagner at the University of Arizona's Steward Observatory used an instrument called NIR, a thermal infrared coronagraph, installed on the Very Large Telescope's Unit Telescope 4 at the European Southern Observatory in Chile. NIR was specifically designed and optimized for one purpose: searching for planets in the habitable zones of Alpha Centauri A and B. The instrument was the product of a collaboration between ESO and Breakthrough Watch, the observational arm of the Breakthrough Initiatives program. It was, in a very real sense, built to answer the question of whether the nearest Sun-like stars host habitable zone worlds. Wagner's team observed the Alpha Centauri system for roughly 100 hours over a period of several weeks. This was an enormous investment of telescope time on one of the most oversubscribed observatories in the world. After processing the data, a faint source emerged near Alpha Centauri A at a projected separation of approximately 1.1 astronomical unit. The source was designated Cone. Cone was tantalizing but ambiguous. The observation arc was short, covering only a few weeks. This was not long enough to determine whether the source moved in a way consistent with an orbiting planet. It could have been a genuine planet. It could have been a clump of warm exozodiacal dust, fine particles orbiting in the plane of any debris disk around the star, heated by starlight and glowing faintly in the thermal infrared. It could have been an instrumental artifact, a ghost created by the imperfect subtraction of Alpha Centauri A's overwhelming glare. The team published their results in 2021 in Nature Communications, carefully framing Cone as a candidate that required further investigation. They noted that the source's properties were consistent with a Neptune to Saturn mass planet, but that they could not rule out other explanations. The scientific community received the result with cautious interest but no consensus. Without independent confirmation, Cone remained in limbo, a dot on a processed image that might or might not represent the first directly imaged planet around the nearest Sun-like star. For 4 years, Cone sat in the literature, occasionally cited, occasionally discussed at conferences, but never confirmed and never definitively ruled out. It became one of those results that astronomers file under interesting, if true, a tantalizing hint that lacks the evidentiary weight to change anyone's conclusions. The scientific process requires reproducibility, and Cone had been seen only once. Then Webb observed Alpha Centauri A in August of 2024 and found SOHN. Different telescope, different instrument, different wavelength, different position relative to the star, but the same system, the same host star, and a source whose properties were broadly consistent with a planet in the same mass range as the one Cone had hinted at. The coincidence was impossible to ignore. Now the Webb team asked a new question. Could the 2019 VLT detection and the 2024 Webb detection represent the same object seen at different points in its orbit? If SOHN and Cone are the same planet, the combined observations constrain its orbital parameters far more tightly than either detection alone. The team incorporated both detections and both non-detections into their orbital models and found that a single coherent world could explain all 4 data points. A gas giant with a mass between roughly 90 and 150 Earth masses, a radius close to that of Jupiter, an orbital period between 2 and 3 years, and an orbital eccentricity of about 0.4. The orbit would be significantly elliptical, carrying the planet from roughly 1 astronomical unit at closest approach to roughly 2 astronomical units at its farthest point from the star. 2 inconclusive detections and 2 non-detections. Individually, none of these observations constitutes a discovery. Together, they sketch the outline of a world that appears and disappears on a schedule consistent with orbital motion. The pattern is suggestive. It is coherent. It is not proof. Charles Beichmann, executive director of the NASA Exoplanet Science Institute at Caltech and co-lead author of the study, framed the significance carefully. Any exoplanets found in the Alpha Centauri system would offer the best opportunity to collect data on planetary systems other than our own, he noted. The proximity of the system means that if this planet is real, every subsequent observation, every spectroscopic measurement, every attempt to study its atmosphere or detect moons becomes easier than for any other known exoplanet. The scientific payoff of confirmation would be immense, but confirmation requires redetection. The team's orbital models make a specific testable prediction. If SOHN and Cone represent the same real planet on the orbit their simulations favor, the planet should swing back to a position visible to Webb's coronagraph in August of 2026. The team has expressed hope of securing Webb observing time to look again during that window. If the planet reappears at the predicted position, the case for its reality strengthens enormously. If it does not, the hypothesis weakens, though it might not die entirely, depending on the orbital geometry. As of now, we're in the gap between detection and confirmation. The planet candidate is real, in the sense that the data supporting it are genuine and have survived rigorous analysis. It is not real in the sense that it has been independently confirmed as a world, rather than an artifact, a dust clump, or some other astrophysical source. The team has been transparent about this ambiguity, and the broader astronomical community has responded with a mixture of excitement and Eric Agol, an astrophysicist at the University of Washington who was not involved in the study, captured the cautious perspective precisely. He has seen planet candidates come and go, he noted. The history of exoplanet science includes plenty of signals that looked compelling initially, but dissolved under further scrutiny. Caution is warranted. But Stanimir Metchev, Canada Research Chair in Extrasolar Planets at Western University offered a different emphasis. The orbital prediction comes with a strict test. The planet should be visible again in 2026 or 2027. These follow-up observations will be key, and assuming the planet is there, he added, it would be the most significant Webb discovery to date. Both perspectives are valid, both are necessary, and the tension between them is itself the point. This is not a story with a clean ending. It is a story suspended in uncertainty, and that uncertainty is precisely what makes it disturbing. Because here is what the data have already revealed, regardless of whether SON turns out to be a planet. Webb looked at the nearest Sun-like stellar system with the most powerful mid-infrared space observatory ever built. It used a coronagraph to suppress starlight, a custom observing sequence to overcome the target's extreme brightness, and advanced computational pipelines to subtract the glare of two stars. After all of that effort, after pushing the instrument to its operational limits, the result was not a clean, obvious detection. It was not a planet standing out unmistakably against a dark background. It was a faint smudge, 10,000 times dimmer than the star, visible in one observation window and absent in the next two, consistent with a real world, but not conclusively distinguishable from noise. This is what the nearest Sun-like star looks like when you finally have the technology to peer beneath its glare. Not simple, not clean, not familiar. Ambiguous, contested, and deeply resistant to interpretation. The system that everyone assumed we would understand first turns out to be one of the hardest to read. The proximity that was supposed to be our greatest advantage became our most persistent obstacle. And the observation that was supposed to bring clarity instead delivered a mystery that will take years, possibly decades, to fully resolve. The August 2026 observation window is approaching. If Webb looks again and the planet reappears, the story enters a new chapter. If it does not, the mystery deepens. Either way, what has already been established is unsettling enough on its own. We finally looked beneath the glare of our nearest sun-like neighbour, and what we found was not the reassuring simplicity we expected. It was a faint, vanishing signal from a world that may or may not exist, orbiting a star we thought we knew, in a system that has been hiding its secrets in plain sight for as long as we have been watching. What that means for every other star system we think we understand is a question with implications far larger than a single disappearing planet. Here is something that most people never consider about astronomy. Distance usually makes everything harder. The farther away an object is, the fainter it appears, the smaller it looks, the fewer photons reach your detector, and the less information you can extract. This is why telescopes keep getting bigger. Larger mirrors collect more light from faint, distant sources. More powerful instruments resolve finer details across greater gulfs of space. The entire history of observational astronomy is a story of building better tools to overcome the tyranny of distance. Alpha Centauri breaks this pattern so thoroughly that it exposes a blind spot in how most people think about cosmic observation. For this system, proximity does not help, it hurts. And understanding why it hurts requires examining each of the major planet detection methods and watching them fail, one by one, against the specific challenges that the nearest sun-like stellar system presents. Start with radial velocity. This is the workhorse technique that has discovered more exoplanets than any other method. The principle is elegant. When a planet orbits a star, its gravity tugs the star very slightly in the opposite direction. The star does not remain stationary while the planet circles around it. Instead, both the star and the planet orbit their shared center of mass. For a massive star and a small planet, the star's wobble is tiny, but detectable. As the star moves toward Earth, its light shifts slightly toward blue wavelengths. As it moves away, the light shifts toward red. By measuring these Doppler shifts with extreme precision, astronomers can detect the gravitational fingerprint of an unseen planet. This method works brilliantly for single stars. Point a spectrograph at a quiet, sun-like star. Monitor its radial velocity over months or years, and any planetary companion will reveal itself as a periodic wobble. The technique has discovered planets ranging from super-Jupiters to worlds only a few times the mass of Earth. It is reliable, well understood, and backed by decades of refinement. Now apply it to Alpha Centauri. Immediately, a problem emerges that does not exist for isolated stars. Alpha Centauri A and B orbit each other. Their mutual gravitational pull creates an enormous radial velocity signal that dwarfs anything a planet could produce. The two stars swing toward and away from Earth on an 80-year cycle, generating Doppler shifts thousands of times larger than the subtle wobble of an orbiting planet. Before you can search for a planetary signal, you must model and subtract the entire binary orbital motion with extraordinary precision. Any error in the binary model, any slight inaccuracy in the predicted positions and velocities of the two stars, leaves residual noise in the data that can mimic or conceal a planetary signal. This is not a theoretical concern. It is exactly what happened in 2012. A team led by Xavier Dumosk used the HARP spectrograph at the European Southern Observatory's La Silla Observatory in Chile to monitor Alpha Centauri B over several years. After subtracting the binary orbital motion, they reported a periodic signal consistent with an Earth-mass planet orbiting every 3.24 days. Alpha Centauri B made headlines worldwide. It was the nearest exoplanet to Earth, orbiting a sun-like star in the system that humanity had dreamed of visiting. Within 2 years, independent analyses revealed that the signal was almost certainly spurious. The binary subtraction had introduced subtle, systematic errors that, combined with the observing cadence and the way data points were sampled over time, created a ghost signal that looked exactly like a planet. Different statistical methods applied to the same data produced different results. Some analyses found the signal, others did not. The planet evaporated under scrutiny, leaving behind a cautionary tale about the dangers of searching for tiny signals buried beneath enormous systematic noise. The lesson was painful but clear. Radial velocity planet searches in tight binary systems are fundamentally harder than searches around isolated stars. The binary creates a wall of noise that must be subtracted before the search even begins, and the subtraction itself introduces uncertainties that contaminate the very signal you are trying to find. Subsequent radial velocity surveys of Alpha Centauri have pushed sensitivity further, using newer instruments like Espresso on the Very Large Telescope, but the binary contamination remains a persistent obstacle. As of today, no radial velocity detection of a planet around either Alpha Centauri A or B has survived independent confirmation. Now consider transit photometry, the method that has produced the largest catalogue of confirmed exoplanets thanks to missions like Kepler and TESS. Transit detection is conceptually simple. If a planet's orbit is oriented so that it passes between its star and Earth, the planet blocks a tiny fraction of the starlight, creating a measurable dip in brightness. The depth of the dip reveals the planet's size. The timing reveals its orbital period. The method is powerful, systematic, and capable of surveying thousands of stars simultaneously. For Alpha Centauri, transit photometry faces a unique geometric problem. The probability that any given planet's orbit is aligned for transits as seen from Earth depends on the ratio of the star's diameter to the planet's orbital distance. For a planet orbiting at 1 astronomical unit from a sun-like star, the transit probability is roughly 0.5%. This means that even if every sun-like star hosted a planet at that distance, only about 1 in 200 systems would show transits. For Alpha Centauri specifically, unless a planet happens to orbit in exactly the right plane, we will never see a transit. There is nothing we can do about this. The geometry is fixed by the planet's orbital orientation, which we cannot control or predict in advance. But the problem goes deeper than probability. Even if a transit did occur, detecting it against Alpha Centauri's brilliance would be enormously difficult. The stars are so bright that photometric precision becomes limited by systematic effects rather than photon noise. Tiny variations in detector response, atmospheric conditions for ground-based telescopes, and instrumental drift create fluctuations that can swamp or mimic a transit signal. The transit of an Earth-sized planet across Alpha Centauri A would produce a brightness dip of roughly 0.01%. Detecting that against the noisy baseline of one of the brightest stars in the sky requires precision that current instruments struggle to achieve for targets this luminous. A dedicated mission called TOLE-MAN has been proposed specifically to search for transiting planets in the Alpha Centauri system using astrometric techniques rather than photometry. But this mission remains in development, and the detection challenge illustrates the broader point. Standard methods that work beautifully for fainter, more distant stars hit fundamental walls when applied to the nearest and brightest sun-like system. This brings us to direct imaging, the method Webb used. Direct imaging bypasses many of the problems that plague radial velocity and transit searches. Instead of detecting a planet's indirect influence on its star, you photograph the planet itself. You see it as a separate point of light, resolved from the host star. No need to subtract binary orbital noise. No need for favourable geometric alignment. If the planet is there and bright enough, and if you can suppress the starlight sufficiently, you see it. But direct imaging introduces its own class of problems that are uniquely severe for Alpha Centauri. The core challenge is contrast. A planet shines only by reflecting starlight or by emitting its own thermal radiation. Either way, it is vastly fainter than its host star. For a gas giant in the mid-infrared, the contrast ratio against a sun-like star is roughly 10,000 to 1. For a rocky Earth-sized world, the ratio climbs to over 1,000,000 to 1 in the mid-infrared and billions to 1 in visible light. Suppressing the star's light enough to reveal such faint companions requires coronagraphs of extraordinary quality, telescopes of exceptional stability, and observing conditions of remarkable precision. Alpha Centauri makes every one of these requirements harder. The stars are so bright that even tiny imperfections in the coronagraph allow enough starlight to leak through and create artifacts comparable in brightness to a planet. The binary configuration means two stars contribute contaminating light rather than one. The system's rapid proper motion across the sky, a consequence of its proximity, requires the telescope to track at unusual rates, complicating the stability of the optical alignment. And the limited angular separation between the two stars means their diffraction patterns overlap, creating a zone of confusion where real sources become nearly impossible to distinguish from optical ghosts. The Webb team overcame these obstacles through ingenuity and brute computational force, but the fact that they succeeded in detecting a candidate while failing to definitively confirm it tells you everything about the difficulty involved. They pushed the most powerful space telescope ever built to its operational limits and came away with an ambiguous result. Not because the telescope is inadequate, but because Alpha Centauri is that hard. And here is the aspect of this difficulty that should genuinely unsettle anyone who thinks carefully about it. If a Saturn-mass gas giant can hide in the habitable zone of the nearest sun-like star, appearing once and vanishing twice in Webb observations, what else could be there that we cannot see at all? Consider the sensitivity limits of Webb's MIRI coronagraph at Alpha Centauri's distance. The August 2024 observation detected SOHN at a brightness roughly 10,000 times fainter than the star. That sensitivity is sufficient to detect gas giants, worlds comparable to Saturn or larger, but it is nowhere near sufficient to detect smaller planets. Uncantably, a Neptune-sized world would be significantly fainter. A super-Earth would be fainter still. An Earth-sized rocky planet would be so dim in the mid-infrared that it would fall far below Webb's detection threshold, invisible regardless of how perfectly the data processing performed. To understand the scale of what might remain invisible, consider what our own solar system would look like to an astronomer at Alpha Centauri trying to observe us with a telescope comparable to Webb. From 4.3 light-years away, our Sun would appear as a bright G-type star, broadly similar to Alpha Centauri A. An observer using a mid-infrared coronagraph equivalent to MIRI could in principle detect Jupiter. At 15.5 microns, Jupiter's thermal emission would place it above the detection threshold. Assuming the coronagraph performed well and the observer's processing pipeline successfully subtracted the Sun's residual glare, Saturn would be a marginal detection, right at the edge of what the instrument could achieve. Beyond that, everything else in our solar system would be invisible. Uranus and Neptune would fall below the sensitivity limit. Earth, Mars, Venus, and Mercury would be utterly undetectable, thousands of times too faint to register even as noise in the processed data. An Alpha Centauri astronomer using Webb-class technology to observe our Sun would conclude at best that one gas giant probably exists and a second one might exist. They would know nothing about the four rocky inner planets. They would have no evidence for the asteroid belt, the Kuiper belt, or the Oort cloud, they would be completely unaware that one of those invisible rocky worlds harbours a biosphere nearly 4 billion years old. Their census of our planetary system would capture roughly 30% of the total planetary mass and 0% of the worlds where conditions permit liquid water. That is exactly the situation we face when observing Alpha Centauri A. We are the astronomer on the other side of the gap, squinting through a coronagraph at a bright sun-like star, capable of detecting only the most massive and thermally luminous members of whatever planetary system might exist. Everything smaller than Saturn is beyond our reach. Everything cooler than a few hundred degrees is lost in the noise. The worlds that would matter most for the question of habitability, rocky planets in the inner habitable zone, are precisely the ones we cannot see. This is not a failure of Webb. It is a statement about the current frontier of what is technologically possible when observing bright, nearby sun-like stars. The frontier will advance. Roman's coronagraph will push sensitivity deeper. Extremely large ground-based telescopes will resolve smaller angular separations. Future space missions purpose-built for direct imaging of Earth-like planets around nearby stars, concepts like the Habitable Worlds Observatory, could eventually detect rocky worlds at Alpha Centauri if they exist. But those missions are decades away. For now, we are limited to seeing the largest inhabitants of a system that could contain an entire, unseen family of smaller worlds beneath the surface of our detection capability. This means that even if Alpha Centauri A hosts a complete planetary system, with rocky inner worlds, gas giants in the middle, and ice giants further out, Webb would detect at most the largest members. The smaller planets would remain hidden, not because they are absent, but because our best instrument cannot see them yet. The system could contain an entire architecture of worlds that we are technologically incapable of detecting at present. And there is another possibility that complicates the picture further. Son might not be a planet at all. One of the competing explanations that the team carefully considered is exozodiacal dust. In our own solar system, fine particles of rock and ice left over from cometary activity and asteroid collisions orbit the Sun in a diffuse disk concentrated near the ecliptic plane. This zodiacal dust is warm enough to glow faintly in the infrared, and it is visible from Earth as a subtle cone of light sometimes seen after sunset or before dawn. If Alpha Centauri A has its own version of this dust cloud, and most Sun-like stars are expected to, that dust would glow at mid-infrared wavelengths and could produce compact brightness features that mimic the appearance of a faint point source in coronagraphic images. The team addressed this possibility directly. They used their observations to place upper limits on the amount of exozodiacal dust around Alpha Centauri A. Their analysis constrained the dust level to no more than roughly a few hundred times the density of our own solar system's zodiacal cloud, a limit that is itself a scientifically valuable result. But this upper limit does not eliminate dust as a possible explanation for SOHN. A moderately dense clump of warm dust at the right position could produce a signal consistent with what was observed, appearing as a compact bright source in one epoch, and dissipating or shifting below detectability in subsequent observations as the dust redistributes along its orbit. Distinguishing between a planet and a dust feature in mid-infrared coronagraphic data is genuinely difficult. Both emit thermal radiation at similar wavelengths. Both can appear as compact sources at similar separations from the star. The critical difference is persistence and orbital motion. A planet follows a predictable orbit, reappearing at calculable positions over time. A dust clump can dissipate, reform, or shift in brightness unpredictably. This is another reason why redetection at the predicted orbital position is so important. A planet will obey orbital mechanics. Dust will not. If SOHN reappears precisely where the orbital models predict, the dust hypothesis effectively dies. If it appears somewhere else, or not at all, dust remains a viable and perhaps favoured explanation. The team's own language reflects this unresolved tension. Even if the planet turns out to be something else, they noted, the observations demonstrate what Webb's MIRI coronagraph can achieve at Alpha Centauri and establish the technical framework for deeper searches in the future. The observation is valuable regardless of what SOHN turns out to be. But the difference between a confirmed planet and a dispersing dust clump is the difference between a historic milestone and a sobering lesson in the limits of current technology. This is not speculation. It is an observational fact about the current limits of instrumentation, and it applies specifically because Alpha Centauri is so bright. For a fainter star at greater distance, the contrast requirements are paradoxically easier to meet in some regimes. The star contributes less contaminating light, the coronagraph performs better relative to the target brightness, and smaller planets become relatively easier to isolate. Alpha Centauri's proximity, which should be an advantage, becomes a handicap that actively prevents us from seeing the very worlds we most want to find. Now, add another layer of complexity. The candidate planet Sohn, if real, does not behave like a planet in a quiet, well-ordered system. Its orbit is elliptical, with an eccentricity of approximately 0.4. This means it does not trace a neat circle around Alpha Centauri A. It swoops inward to roughly 1 astronomical unit, then swings outward to roughly 2 astronomical units, alternately entering and leaving the habitable zone. This orbital shape is itself puzzling, because gravitational interactions with Alpha Centauri B should circularize planetary orbits over time. A planet maintaining significant eccentricity in a tight binary system raises immediate questions about how it got there and what keeps it on that path. Even more unusual is the planet's apparent orbital inclination. The simulations suggest the orbit is tilted by roughly 50 to 130 degrees relative to the orbital plane of the Alpha Centauri A and B binary. In a well-behaved planetary system that formed from the same disk of material as its host stars, planets should orbit roughly in the plane of the binary. A large tilt suggests either the planet formed through an unusual process, was gravitationally scattered into its current orbit by interactions with other bodies, or was captured from somewhere else entirely. Each of these scenarios has profound implications for planet formation theory. The existence of a gas giant in this system would challenge current models in a fundamental way. Theoretical studies of planet formation in binary star systems have long predicted that the gravitational influence of a stellar companion truncates the protoplanetary disk around each star, limiting the amount of material available for planet building. For a binary with the orbital parameters of Alpha Centauri A and B, the stable zone around each star extends only to a few astronomical units. Beyond that distance, the companion star's gravity destabilizes orbits and prevents long-term planetary survival. A Saturn-mass planet, orbiting at 1 to 2 astronomical units, sits right at the boundary of this stability zone. Its existence would mean that planet formation proceeded successfully in a region where dynamical models predicted it should be marginal at best. Either the models underestimate the resilience of planetary formation in binary systems, or this planet's history involves migration, scattering, or other dynamical processes that placed it in an orbit that formation alone could not explain. The researchers themselves acknowledge this tension. The planet's very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments, Arnie Ketsangi stated. And here lies something crucial that most coverage of this discovery has overlooked. The observational difficulty is not a flaw in the narrative. It is the narrative. The fact that the nearest Sun-like system is this hard to interpret, even with the most advanced space telescope ever built, is itself the most important result of the observation. Think about what this means in the broader context of exoplanet science. Over the past 3 decades, astronomers have built an increasingly detailed picture of planetary systems across the galaxy. We know that planets are common. We know that roughly 1 in 5 Sun-like stars hosts a rocky planet in its habitable zone. We know that planetary architectures vary enormously, from tightly packed systems of super-Earths to lonely gas giants on wide orbits. We have statistical frameworks that describe the frequency and distribution of planets across stellar types, orbital distances, and size ranges. But all of these statistics are built from observations of distant stars. Stars tens, hundreds, or thousands of light years away. Stars faint enough that our instruments can work effectively against their glare. The nearest Sun-like system, the one that should anchor our understanding with the most detailed data available, has contributed essentially nothing to this statistical framework. We have no confirmed planets around Alpha Centauri A or B. We have one candidate that appeared and vanished. We have upper limits on what might or might not exist. And we have a set of technical challenges that make every observation an ordeal. This absence is not merely an inconvenience. It represents a genuine gap in our knowledge that biases how we think about planetary systems. Every model of planet occurrence, every estimate of habitable world frequency, every projection of how common life might be in the galaxy is built on data that excludes the nearest and most important test case. We are extrapolating from distant observations without knowing whether the closest system follows the same rules. If Alpha Centauri A hosts a gas giant in its habitable zone, that changes the statistical picture. Gas giants in habitable zones are not common around Sun-like stars based on current surveys. Finding one at the nearest Sun-like star would either represent remarkable coincidence or suggest that such planets are more common than existing surveys indicate, with many hiding below detection thresholds in more distant systems. Either interpretation has significant consequences for our understanding of planetary demographics. If the candidate turns out to be something other than a planet, a clump of exozodiacal dust, an unresolved background object, or an artifact that survived the team's analysis, the implications are different, but equally important. It would mean that even Webb's most determined and technically sophisticated observation could not cleanly resolve the nearest Sun-like stellar neighborhood. The system would remain a blank spot on our exoplanet map, a maddening void at the one location where we most expected clarity. The upcoming observation window is therefore more consequential than most people realize. If Webb observes Alpha Centauri A again in August of 2026, and the planet reappears at the position predicted by the orbital models, the case for its reality becomes very strong. A detection at the predicted location and brightness would constitute independent confirmation through redetection, the standard of evidence the community requires. The planet would graduate from candidate to near certainty, pending final verification. What makes redetection so powerful as a confirmation method is that it tests a prediction rather than merely repeating an observation. The team's orbital models do not simply say the planet should be visible again at some unspecified future date. They predict a specific range of positions and brightnesses for specific observation windows based on the orbital parameters derived from the combined 2019 and 2024 data. If the planet appears at a position consistent with those predictions, the probability that the detection is coincidental drops dramatically. A random artifact or noise fluctuation has no reason to appear at the predicted location. A real planet on a real orbit does. This prediction and test framework is the backbone of the scientific method, and it gives the August 2026 window a significance that transcends a simple reobservation. It is a genuine experimental test of a quantitative hypothesis. The orbits say the planet should be here, at this brightness, at this separation. Either it is, or it is not. The answer, whichever way it falls, will be decisive in a way that no amount of reprocessing existing data can achieve. If the planet does not reappear, the hypothesis weakens considerably. The team would need to explore whether the original detection could be explained by other phenomena. The candidate might not die immediately. Some orbital configurations could still explain a non-detection, but the burden of proof would shift heavily against the planetary interpretation. Beyond Webb, additional confirmation pathways exist. The Nancy Grace Roman Space Telescope, currently expected to launch by 2027, carries a coronagraph specifically designed for direct imaging of exoplanets around nearby stars. Roman's coronagraph is more advanced than Webb's MIRI coronagraph, with better starlight suppression capabilities in certain regimes. If the Alpha Centauri planet is real, Roman should be able to confirm and characterize it with independent instrumentation. Ground-based extremely large telescopes currently under construction, with mirrors exceeding 30 meters in diameter, will also bring new direct imaging capabilities that could resolve the Alpha Centauri system in unprecedented detail. But all of these future instruments share a common reality. They will face the same fundamental challenge that Webb faced. Alpha Centauri is bright. The binary creates dual-source contamination. The proximity that makes the system scientifically valuable is the same proximity that makes it observationally hostile. Better instruments will push the detection limits deeper, potentially revealing smaller planets and more detailed orbital characterization, but they will not eliminate the underlying difficulty. The nearest Sun-like system will remain one of the hardest targets in the sky for as long as its stars keep burning. There is one factor that makes this particular moment in time uniquely important for observing Alpha Centauri, and most people outside professional astronomy have no idea it exists. Alpha Centauri A and B orbit each other every 79.9 years on an elliptical path. As they revolve around their shared center of gravity, their apparent separation on the sky, as seen from Earth, changes dramatically. At their widest, the two stars sit roughly 22 arc-seconds apart. At their closest, they squeeze to approximately 4 arc-seconds. That closest approach occurred around 2016. At 4 arc-seconds of separation, the two stars are so tightly packed on the sky that their diffraction patterns and scattered light merge into a single unresolvable mess in most instruments. Coronagraphic observations during this period were essentially impossible. Even blocking one star left the other's glare smeared directly across the region where planets would be found. The worst possible window for direct imaging coincided with some of the most sensitive instruments in history coming online. Since 2016, the stars have been widening again. By August of 2024, when Webb observed the system, the separation had grown to roughly 10 arc-seconds, enough breathing room for the coronagraph to block Alpha Centauri A, while keeping Alpha Centauri B far enough away that its contamination, while still severe, could be computationally subtracted rather than hopelessly entangled. The separation will continue increasing through the 2030s and 40s, reaching maximum again around 2055. This means the current decade and the next represent the most favourable observational window in the binary's 80-year cycle for direct imaging planet searches. Webb's observation was not just ambitious in the abstract. It was strategically timed to exploit a window that did not exist 10 years ago and that will only improve gradually over the coming 2 decades. The August 2026 follow-up, if it happens, falls within this same favourable period. So would observations by the Nancy Grace Roman Space Telescope after its expected launch. The alignment of improving instrumentation with widening binary separation creates a convergence of opportunity that is genuinely rare. If we do not characterize Alpha Centauri's planetary system during this window, the next equally favourable period lies decades in the future, and this is perhaps the most counterintuitive lesson of the entire story. We tend to assume that the closest objects are the easiest to study. In everyday life, this is true. You can examine something in your hand more easily than something across the room. You can study your own neighbourhood more thoroughly than a city on the other side of the world. But stellar systems do not follow this intuition. The closest sun-like stars are the brightest, and brightness creates problems that distance does not. A star 100 light-years away is faint enough that its light does not overwhelm sensitive instruments. A star 4 light-years away blazes so fiercely that it blinds the very tools designed to study what orbits it. This inversion of the expected relationship between proximity and observability is not a minor technical footnote. It fundamentally shapes what we know and do not know about the nearest regions of the galaxy. The systems we can study most easily are not the closest ones. They are moderately distant systems, where the balance between brightness and angular separation favours our instruments. The closest systems remain paradoxically opaque, their secrets locked behind walls of light that we are only now beginning to learn how to penetrate. Alpha Centauri sits at the extreme end of this paradox. It is the nearest major stellar system. It contains the nearest sun-like stars. It is the default destination for every interstellar travel concept humanity has ever seriously proposed. And yet, after centuries of observation and the deployment of the most powerful space telescope ever constructed, we still cannot say with certainty whether it contains even one planet. The system we assumed we would understand first may turn out to be one of the last we fully resolve. And the candidate planet that appeared in Webb's data, flickering once into visibility before retreating behind a wall of glare, may be the first hint that Alpha Centauri has been holding back far more than anyone imagined. What that possibility means for how we think about the nearest sun-like stars, and for how much hidden structure may be waiting in stellar systems we have barely begun to explore, reshapes the most basic assumptions about our place in the galaxy. There is a word in the title of this story that deserves careful attention. The word is disturbing. It does not mean what most people assume when they read it next to a phrase about space. It does not mean frightening in the way a horror film is frightening. It does not mean dangerous. It does not mean that Alpha Centauri harbors some cosmic threat lurking 4 light-years away, waiting to harm us. The disturbance here is quieter than that, subtler, and in many ways more profound. What James Webb's observation of Alpha Centauri was not was our safety. It was our assumption. The assumption that the nearest major Sun-like stellar system should be among the most understood places in the sky. The assumption that proximity equals knowledge. The assumption that if we have been staring at something for thousands of years, we must know what we are looking at. Webb's data did not confirm that assumption. They dismantled it. And what remains after the dismantling is a picture of the nearest Sun-like stellar neighborhood that is less familiar, less resolved, and less comforting than almost anyone expected. Consider what we actually know about the Alpha Centauri system right now. After everything Webb has done, we know the basic properties of the 3 stars. We know their masses, luminosities, temperatures, ages, and orbital parameters. This information has been refined over decades and is well established. But when it comes to the most important question, whether planets exist around the 2 Sun-like stars, we have almost nothing confirmed. 3 planets orbit Proxima Centauri, the dim red dwarf member of the system. 0 confirmed planets orbit Alpha Centauri A. 0 confirmed planets orbit Alpha Centauri B. And 1 candidate, SOHN, appeared once in Webb's mid-infrared data and vanished in 2 follow-up observations. This is the state of our knowledge about the nearest Sun-like stellar system. Not ignorance, exactly. We have mountains of stellar data. But on the question that matters most for understanding whether the nearest Sun-like stars resemble our own, whether they host worlds, whether those worlds could be characterized, whether the system represents a template for what Sun-like planetary systems look like up close, we have an incomplete answer suspended in ambiguity. And the ambiguity itself is the disturbance, because it reveals something about the relationship between proximity and understanding that most people have never confronted. We assume these 2 things travel together. Closer means clearer. Nearer means more knowable. If a friend lives next door, you know more about them than a stranger across the city. If a building sits at the end of your street, you know its shape better than a skyscraper on the other side of town. This intuition is so deeply embedded in human cognition that we apply it to stars without questioning it. Alpha Centauri is close, therefore we must understand it. This reasoning feels unassailable, but stars are not friends, and the galaxy is not a neighborhood in the human sense. In stellar astronomy, proximity brings brightness, and brightness brings glare. The closer a Sun-like star is, the more intensely its light floods our instruments, creating walls of photonic noise that conceal rather than reveal what surrounds it. Distance, paradoxically, offers clarity. A Sun-like star 50 light-years away is dim enough that coronagraphs can suppress its light effectively, that radial velocity signals can be extracted cleanly, that transit measurements can achieve the required precision. The nearest Sun-like star, blazing as the 3rd brightest point in the entire sky, defeats these same techniques through sheer luminous force. The sharpest way to feel this paradox is to compare Alpha Centauri with other nearby stellar systems that have been far more cooperative. Consider TRAPPIST-1, a dim, ultra-cool red dwarf star sitting roughly 40 light-years from Earth. TRAPPIST-1 is nearly 200 times smaller than the Sun and over 2,000 times fainter. It is so dim that you cannot see it with the naked eye even from the darkest site on Earth. And yet, astronomers have confirmed 7 rocky planets orbiting this star, 3 of them in the habitable zone. Webb is already performing transmission spectroscopy on these worlds, passing starlight through their atmospheres during transits to search for molecular signatures. We know more about the atmospheric composition of planets 40 light-years away, around a star most people have never heard of, than we know about whether any planet exists around the nearest Sun-like star, 4 light-years away. Or consider Epsilon Eridani, a K-type star 10.5 light-years from Earth. This star hosts at least 1 confirmed planet, Epsilon Eridani b, a gas giant roughly the mass of Jupiter, orbiting at 3.4 astronomical units. The planet was detected through radial velocity measurements and later confirmed by astrometric observations. Epsilon Eridani is a single star. which means its radial velocity signal is clean, uncontaminated by binary orbital noise. The detection was straightforward by modern standards. One star, one clean signal, one confirmed planet. TORS-AT, a G-type star just 12 light-years away, has yielded multiple planet candidates through radial velocity surveys. The signals are debated, with some studies claiming 4 planets and others finding fewer. But the point is that the data are tractable. TORS-AT is a single star. Its radial velocity baseline is clean. Astronomers can search for planetary signals without first subtracting the enormous gravitational signature of a binary companion. Even closer, at 6 light-years, sits Barnard's star, a red dwarf with a candidate planet detected through radial velocity in 2018, though that detection remains contested. Ross 128, at 11 light-years, hosts a confirmed super-Earth in its habitable zone. GJ 887, at 10.7 light-years, has 2 confirmed super-Earths detected by radial velocity. The pattern is unmistakable. Single stars, even relatively nearby ones, have yielded planets through standard techniques. Dim stars, even ones much farther away, have yielded entire planetary systems. The one system that has resisted all of these methods is the nearest Sun-like binary. Alpha Centauri's twin obstacles, brightness and binarity, create a unique combination of challenges that no other high-priority target shares to the same degree. This comparison does more than illustrate a technical point. It reveals a structural bias in our knowledge of the nearest stellar neighborhood. We know the planetary inventory of dim, distant red dwarfs far better than we know the planetary inventory of the nearest Sun-like stars. Our map of the local galaxy has a hole in it at exactly the location where the information would be most valuable. The star system most relevant to the question of whether Sun-like stars commonly host planets, the one where any detection would carry the greatest scientific weight, is precisely the one that remains unresolved. This is not a temporary technological limitation that will vanish with the next generation of instruments. It is a structural feature of how observation works for nearby bright targets. Better telescopes will push detection thresholds deeper. The Nancy Grace Roman Space Telescope, with its advanced coronagraph, will probe regions of the Alpha Centauri system that Webb cannot reach. Extremely large ground-based telescopes will offer angular resolution and light-collecting power beyond anything currently available. Each new instrument will peel back another layer, but the fundamental tension between proximity and brightness will remain. Alpha Centauri will always be one of the most technically challenging targets in the sky, precisely because it is one of the closest. And this means that the system we treat as the most knowable will likely be one of the last to yield its full secrets. The planets of TRAPPIST-1, a dim red dwarf 40 light-years away, are already being studied spectroscopically by Webb, their atmospheres probed for chemical signatures. Planets around dozens of other stars at distances of 10 to 50 light-years are yielding to transit and radial velocity surveys. But the nearest Sun-like system remains stubbornly opaque, its planetary inventory unknown, its architecture uncharted, its habitability unexplored. The cosmic address we thought we knew best turns out to be the one we can read least clearly. Now consider what it would mean if the planet candidate is confirmed. If SOHN is real, if Webb or Roman or a ground-based giant telescope redetects it at the predicted position and brightness, the implications ripple outward in multiple directions simultaneously. First, it would mean that a gas giant, roughly the mass of Saturn, orbits inside the habitable zone of the nearest Sun-like star. This is remarkable on its own. Gas giants in habitable zones are not common based on current exoplanet surveys. Finding one at the nearest Sun-like star, the very first place you would check, would immediately raise questions about whether such planets are more widespread than existing statistics suggest. Perhaps many Sun-like stars host similar worlds that have simply evaded detection because our surveys are not sensitive enough. Perhaps the frequency of gas giants in habitable zones has been systematically underestimated. One confirmed detection cannot settle this question, but it would reframe how astronomers think about planetary demographics around Sun-like stars. Second, the planet's orbital properties, its eccentricity, its inclination relative to the binary plane, would challenge existing models of planet formation in binary star systems. Current theory predicts that the gravitational influence of a stellar companion truncates protoplanetary disks, limits the supply of planet-building material, and destabilizes orbits beyond a certain distance. A gas giant surviving in the marginally stable zone of a tight binary would demonstrate that planet formation is more resilient, more creative, and more capable of producing unexpected outcomes than our models currently allow. Theorists would need to explain how this planet formed, how it achieved its eccentric and inclined orbit, and how it has survived for billions of years in a gravitationally hostile environment. Third, and perhaps most provocative, a confirmed gas giant would raise the question of what else orbits Alpha Centauri A. Gas giants do not typically exist alone. In our own solar system, Jupiter and Saturn coexist with 4 rocky inner planets, 2 ice giants, a belt of asteroids, a belt of comets, and a vast population of smaller bodies. If Alpha Centauri A hosts a Saturn-mass planet, it could also host smaller worlds that remain below current detection thresholds. Rocky planets in the inner habitable zone, ice-rich moons orbiting the gas giant itself, belts of debris sculpted by gravitational interactions with the binary companion. The detection of one planet would transform Alpha Centauri A from a system with 0 known worlds to a system where an entire hidden architecture becomes plausible. But now consider the opposite outcome. Suppose Webb observes Alpha Centauri A again in August of 2026, and the planet does not reappear. Suppose subsequent observations by Roman and ground-based telescopes also fail to find it. What would that mean? It would not necessarily mean the original detection was an error. Some orbital configurations could still hide the planet during specific observation windows, but the weight of evidence would shift against the planetary interpretation. The candidate might be reclassified as a probable artifact, a clump of exozodiacal dust, or a statistical fluctuation that passed the team's tests by chance. The system would revert to its previous status. 0 confirmed planets around Alpha Centauri A, 0 confirmed planets around Alpha Centauri B, a pair of sun-like stars sitting 4 light-years away with nothing to show for decades of searching. And that outcome, if it comes, would be disturbing in its own way. It would mean that even Webb's most heroic effort could not decisively resolve the nearest sun-like stellar neighborhood. It would confirm that the system remains beyond our ability to characterize with current technology, not because the technology is primitive, but because the target is uniquely resistant to observation. The blank spot on our exoplanet map would persist, a maddening void at the one location where we most expected information. Either outcome, confirmation, or non-confirmation leads to the same unsettling conclusion. The nearest sun-like stellar system is not what we assumed. It is not a familiar place that we understand and can check off as solved. It is an unresolved question that better instruments keep making more complex rather than more simple. Every time we look at Alpha Centauri with sharper eyes, we do not see a clearer picture. We see more reasons for uncertainty. This pattern, where improved observation reveals hidden complexity rather than clean answers, is not unique to Alpha Centauri, but it finds its most emotionally resonant expression here, precisely because of the system's psychological significance. Alpha Centauri is not just a scientific target, it is a cultural symbol. It represents the nearest shore beyond our solar system, the first stepping stone into the wider galaxy, the cosmic neighbor whose very name carries undertones of familiarity and accessibility. Breakthrough Starshot chose Alpha Centauri as its destination because it is close. Science fiction writers set stories there because it feels reachable. Astronomers prioritize it because it should be the easiest sun-like system to study. An entire mythology of nearness has been built around this system, a mythology that assumes closeness implies knowability, that our next-door neighbor should be the first place we understand and the first place we visit. Webb's observation punctured that mythology, not dramatically, not with a single devastating revelation, but through the slow accumulation of difficulty, ambiguity, and irreducible uncertainty. The telescope did not find something terrifying at Alpha Centauri. It found something harder to process. It found that the nearest sun-like system resists understanding in ways that are specific, structural, and unlikely to be resolved quickly. The comfortable story that Alpha Centauri is basically a solved address waiting for us to visit was always a projection, a story we told ourselves because it felt good, not because the data supported it. What the data actually support is something less comfortable. The nearest Sun-like stellar system may contain worlds we cannot yet see. It may harbour a planetary architecture that has eluded every detection method we have deployed over decades. A gas giant may orbit in its habitable zone on a path so eccentric and inclined that it appears and disappears in our instruments like a phantom. And beneath that candidate gas giant, below the detection threshold of our most powerful telescope, there may be smaller worlds, rocky worlds, moons with subsurface oceans, entire categories of objects that we will not be able to characterize for years or decades to come. The nearest Sun-like neighbour is not empty. It is not solved. It is not waiting passively for us to come look. It is actively difficult, scientifically slippery, and capable of withholding information despite our best efforts to extract it. And if this is true of the system 4 light-years away, consider what it implies about every other stellar system in the galaxy. There are roughly 400 billion stars in the Milky Way. The vast majority have never been observed with anything approaching the sensitivity and resolution that Webb brought to Alpha Centauri. Most Sun-like stars in our galaxy are hundreds or thousands of light-years away, accessible only through indirect detection methods that reveal limited information about planetary properties. We assign statistical probabilities to these distant systems. We estimate how many host habitable worlds based on survey data from missions like Kepler and TESS. We build models of galactic habitability that treat each star as a data point in a vast cosmic census. But the Alpha Centauri results suggest that these models rest on thinner ice than we acknowledge. If the nearest Sun-like system can hide a gas giant in its habitable zone, if it can defeat our best instruments through sheer brightness and binary complexity, then every other system we have studied is even more incompletely characterized. The planets we have detected around distant stars represent the fraction of worlds that happen to transit, happen to produce detectable radial velocity signals, or happen to be bright and separated enough for direct imaging. The planets we have missed, the ones too small, too far from their stars, too faintly emitting, too deeply embedded in stellar glare, may vastly outnumber the ones we have found. This is not a new insight. Astronomers have always known that their surveys are incomplete, but Alpha Centauri gives that incompleteness a visceral, personal quality. It is one thing to acknowledge abstractly that distant stars probably host undetected planets. It is another thing entirely to stare at the nearest Sun-like system and realize that even there, even with the best telescope humanity has ever built, the picture remains fundamentally incomplete. The galaxy is not a collection of solved systems with a few mysteries at the margins. It is a vast archive of hidden structure, where even the most accessible addresses resist full characterization. Every Sun-like star you see in the night sky could host planetary systems as complex and surprising as our own. And we would not know, because the tools we have today can only detect the most conspicuous members of those systems, the largest planets, the closest orbits, the most favorable geometries. Everything else remains in shadow. Alpha Centauri makes this reality personal because it removes the excuse of distance. You cannot blame the incompleteness on the target being too far away. Alpha Centauri is as close as a Sun-like system gets. If we cannot fully characterize it, the limitation is not distance. It is something more fundamental about the nature of observation itself, about the relationship between bright stars and faint planets, about the gap between what our instruments can achieve and what the universe demands. And there is something deeply unsettling about sitting on a planet orbiting one Sun-like star and looking across 4 light-years of space at another Sun-like star. Almost the same age, almost the same mass, almost the same luminosity, and not knowing what orbits it. Our Sun hosts 8 planets, a belt of asteroids, a belt of comets, and at least one world teeming with life. Alpha Centauri A is our Sun's near twin. The question of whether it hosts anything comparable is not idle curiosity. It is a question about whether our solar system is typical or exceptional, whether the conditions that produced Earth are common or rare, whether the galaxy is full of worlds like ours, or whether we exist in unusual isolation. Webb's observation did not answer that question. It opened it wider. It showed that the nearest Sun-like star may host a gas giant in a configuration nobody predicted, on an orbit nobody expected, in a system that has resisted every previous attempt at planetary detection. And behind that candidate gas giant, in the shadows below the detection threshold, there may be more, or there may be nothing. We do not know. And not knowing, when the target is this close and this familiar, is the most disturbing part of the entire story. The James Webb Space Telescope did not find a monster at Alpha Centauri. It did not find aliens, or a Death Star, or a cosmic threat hurtling toward Earth. What it found was worse, in a scientific sense. It found that the nearest Sun-like stellar system is not the comfortable, understood neighbour we imagined. It is a complex, glare-shrouded, dynamically chaotic binary system that can conceal large worlds in its habitable zone and refuse to reveal them even under the most intense observational scrutiny ever applied. It found that proximity does not guarantee familiarity. It found that the house next door has rooms we have never entered, doors we cannot open, and architecture we are only beginning to map. Every clear night, Alpha Centauri rises in the southern sky. It blazes with the steady light of two sun-like stars locked in their ancient gravitational waltz. To the naked eye, it looks like a single bright point, reassuring, familiar, unchanged since the first human looked up and wondered what the stars were. But behind that steady light, beneath that comforting brightness, something may be orbiting. A world roughly the size of Saturn, tracing an eccentric path through the habitable zone, appearing and disappearing in our data like a secret the system is not quite ready to share. And beneath that world, further below the threshold of what our instruments can detect, there may be smaller worlds, harder to find, more consequential for the question of whether we are alone. We named this system, we charted it, we built missions to visit it, we wrote it into our stories as the first place we would go when we finally left home. And when we turned the sharpest eye ever constructed toward it, it did not greet us with clarity. It greeted us with a vanishing point of light and the quiet, persistent suggestion that even the nearest sun-like neighbour has been keeping secrets. The more clearly we look at Alpha Centauri, the less it behaves like a solved address. The more powerful our instruments become, the more the system reveals not answers, but deeper layers of uncertainty. The familiar bright point in the sky is not what we thought it was. It is an open question, still unresolved, still capable of surprise, still reminding us that in this galaxy, proximity was never a promise of understanding. It was only ever an invitation to look more carefully, and we are just beginning to accept that invitation.